Um, so on Thursday, during my tutor session, I talked about the math problem set and some like concepts. Um, but since most of the people were not there on Thursday, I feel like it might be useful to make this video to explain some of the more confusing problems and concepts for the problem set this week. So I guess the first concept that comes up a lot in the problem set is level set. Or level curve or level surface. So what is a level set? To understand level set, let's go back and look at some very easy high school or primary school math. So first of all, how do we find the solution of this equation? Should be fairly easy. X plus 3 equals to 5. You just find whatever x satisfy this equation. You find out that when x equals to 2, this equation stands. So the solution of this equation will be 2. What about this? The solution of this equation, x plus y equals 5. We do a similar thing, but at this time we will not get one specific solution. There will be a bunch of them. Like it can be 1 and 4, it can be 2 and 3, 0 and 2, and basically they're like infinite solutions. But all of them satisfy one restriction. That is, whatever solution it is, when you plug it into x and y, this equation should stand. That is, the solution of this equation will be the set of x and y's, so that when you plug it in, x plus y equals 5. So let's take a step back and think about like this entire process of finding a solution or solution set to an equation. What do we do? So we just see this equation and there are a bunch of variables in it. It's very intuitive to just like try to find all possible variables or like all possible constants to plug into the variable so that the equation stands. So this is how we find solutions. And now if you open up your Evans textbook and look up level set and how it's defined, it's basically defined the same way as finding solutions or solution set to an equation. So level set is basically finding a specific solution set. So level sets of this equation x plus y equals to z are sets of x and y so that the equation stands for a specific well-defined z. Just like what we did when we tried to find the solution to x plus y equals 5, we were finding the set of x and y so that the equation stands for a specific well-defined z, namely 5. So that's it. There's really nothing special about level set. It's just some very old concept that you have been dealing with since middle school, high school math. It's just now like a brand new name, and now we name it level set. There are different types of it. It can be curve or level surface. You shouldn't be confused when you see like levels that come in like different shapes, like curve or surface or whatever dimension it is. But basically, deeply, inherently, all those are the same. So, for example, when we're dealing with a two-dimensional equation like R2, something exists in R2, basically a level set would look like a line or a curve, meaning that every point on this curve, every point you plug in the x and y coordinate into the equation, you get the specific or the same z value. So what about something with a higher dimension? It's not that intuitive how surface work in terms of level surface. So the mathematical definition is basically every point on the surface, you plug in the x, y, and z coordinate, you get the same function value. But then what does it mean by a surface in a four-dimensional function? How can we visualize a four-dimensional function? First of all, if we think of dimensions in this like traditional way of defining dimension, it's really hard, or it's basically impossible to visualize anything higher than 3 dimensions, because we have the x coordinate, y coordinate, z coordinate pointing in like the two horizontal directions and the vertical direction, and then we exhaust all possible directions in the 3-dimensional space that we live in. So there's one trick to try to visualize higher dimensional graphs. We may not. So actually, there's the way we define dimensions or x, y, and z coordinates and how we visualize them are pretty arbitrary. It's just so popularly defined that x points in the horizontal direction and y points in the vertical direction when we plot things on the Cartesian coordinates. But those two don't really necessarily need to be those two directions. We can even introduce something not related to direction at all. For example, if we look at the graph on the left, if we look at this graph right here. So basically we have the x and y and z direction as the three directions traditionally defined. But when we introduce the fourth direction, the fourth dimension, we introduce something called color. Let's introduce color. So color is a pretty well defined dimension. It's like it's independent from x, y, and z direction. Like there's no correlation between horizontal distance or vertical distance and the color we have for each point. But so basically in this graph, at any given point, when we have an x, y, and z direction coordinate, and we plug in those three numbers, what we get is a fourth function value, a fourth dimension, which is the color. So if I plug in like minus 0.4, which is here, like 0.02 here, and like minus 0.02. So that will give us a point somewhere here. And it will output a function value, which is orangish yellow, or something between red and yellow. So that's one way to visualize a four-dimensional function, an R3 to R function. You plug in three numbers, you get one value. You plug in x, y, and z, you get the color. Or it can be something else. Like you can come up with however creative dimensions you can think of. For example, this apple pie. This apple pie exists in the three-dimensional space. There's x, y, and z coordinates, and at any given point, when you have an x, y, and z coordinate, there's like a tiny point or tiny piece of apple pie that's somewhere like buried in here. So that point has a well-defined, first of all, temperature. Maybe it's just baked. Maybe like it's left over. It might be cold, might be warm. So there's a well-defined temperature, and the temperature distribution on this apple pie may not be uniform. Like some point here might be like warmer than some point here. So at any point, there's a well-defined temperature. There's also a well-defined taste. It might be sweet because there's a huge chunk of apple here. It might be like not as sweet on the crust. So this apple pie, when you plug in x, y, and z, it will give you like a whole bunch of other scalars. For example, temperature, taste, texture. So this apple pie we're looking at is basically an R3 to R3. It's like a six-dimensional graph of a function. And without like looking at this apple pie, when you first think about six-dimensional, seven-dimensional graph, no one would tell you it's visualizable. But here you go. Like this apple pie is basically a very high dimension object, and that's an everyday object. And like don't tell yourself that you cannot visualize your four-dimensional thing. Like you can always come up with creative dimensions and try to work your way through. Also, like things like y equals to x, or a two-dimensional function does not need to be on a Cartesian coordinate. You can just think of a one-dimension coordinate like on a string of line, and each point on the line has like a color. And so instead of introducing a y dimension as the vertical distance, I introduce a second dimension as a color. So now instead of having like a y equals to x, instead of having a straight line on the Cartesian coordinates, now I have it's a flat line with a gradually changing color on the line. And the definition of slope will now turn into like how fast the color changes when you go along the line. So there's really no reason why we define x, y, and z as like vertical, horizontal distance, just arbitrarily defined. So back to level curve and level surface. Curve and surface may have their own semantic meaning, but there's really no correlation between like y level curve turn out to be a curve and when you try to visualize it, or a y level surface is a surface when you visualize it. They're all the same. They're basically mathematical sets of points. And when you change the way you plot your graph, like for example from x, y, and z coordinates to like the apple pie way of plotting a function, it will no longer be a curve, but it will still be called a level curve, but it is not a curve. when you try to visualize it. So when you see level curve, it's basically the same thing as level surface. You can just cross out curve, surface, or level anything on your homework or problem set and replace it with level set. And just use the uniform definition of level set. And that will just make things so much easier because things will become the same. You don't need to overthink about like why this is a curve or why this is a surface. It's just a set of points that give you a same function value when you plug it into the function. So another concept that comes up a lot is locus or loci. Loci is the plural form of locus. So basically, they're the set of points that satisfy the given condition, and the condition will be given in the form usually as an equation, like a quadratic equation. And the locus of that quadratic equation will be, in other words, the graph. When you like type in the equation, the Wolfram alpha, it will give you the set of points that satisfy the given condition, which is the quadratic equation, and you'll plot it out in terms of a graph. So in other words, when you think of the graph of y equals to like 2x, it will be a line with a certain slope on the Cartesian coordinates, and those are the points that satisfy the given condition, namely y equals to 2x. So that is the locus of the function. So that will lead us to something called the graph of a function. And remember, there's a problem in the P set that asks you to define what would be a quote-unquote graph of an R2 to R2 function. So we were taught in middle school and high school that like when we try to graph something like on a Cartesian coordinate, we just plot down like the points that satisfy the function. If it is a linear function, we just connect the lines, all those. But then when we have an R2 to R2 function, it's not that readily visualizable. But as we just talked about, we can try to work our way around to think about what this might look like in a real world. So instead of having like a 4-dimensional space that's very abstract and we can now plot it out on a piece of paper, we can instead think of something. So basically R2 to R2, what this function should do is you have two numbers, you plug in two numbers, in this case x and y coordinates, and you get a third and fourth number as the output of the function. So that is how R2 to R2 is defined. So in this case, you have it says radius. I found this online, but like you can think of this as x coordinate, y coordinate. So you plug in x and y coordinates, it will output like a function value, which is the point. For example, if I plug in like this will be 1 and 0, so 0 on x and 1 on y. So at this point right here, there's a corresponding point on this graph with well-defined height, and a well-defined color. In this case, it will be red right here. So you see, like you put in two values, x and y coordinates, you get a third and fourth value. The third value is the height, the fourth value is the color. What if I don't like color? There are other ways. For example, we might. So I talked about this during my first tutor session in week 2. This is a fantastic way to represent an R2 to R2 graph. At any given point, there's an x and y coordinate. You plug in x and y, you get like a given point, for example, this point, and there's a vector at this point. How many values do we need to define a vector? 2. So in this case, we plug in two numbers, x and y coordinates, and we get a third and fourth output, namely the x and y coordinate of the vector. Yeah. What if I don't like vector fields? If like apple pie, we can still use the apple pie. So we have like, for example, x and y coordinates on this plane, and at any given point, there will be like, for example, this tiny cylindrical chunk of apple pie. So at any given point, at any given x and y, there's a unique cylindrical chunk of apple pie, and there's an average temperature and there's an average taste or texture, and that will be our third and fourth output. So there's really nothing special about R2 to R2 function, and the graph of that function will basically just be the so something that is like the locus of the function. So basically, what you plug in, you get two outputs. So the graph will be something containing all these four pieces of information. Just like on this apple pie, the x and y coordinate of any given point, and the texture and temperature, or taste, whichever two you pick, will be stored in this apple pie, and you need nothing else. You just take this pie, carry it around anywhere, and you will not lose any that information of four values. So it takes in two, give you two values. So in total, there will be you need four dimensions or four um, parameters to um, describe this function, and that is a fourth dimension graph. If you think about it like an R to R function, like y equals to 2, you plug in an x value, you get a y value, right? And there's a piece of information referring to the x coordinate and a piece of information referring to the y coordinate. So there are two pieces of information, and when they try to plot this on a piece of paper, it's a two-dimensional thing, right? It's a line that exists in a two-dimensional Cartesian coordinate. You need both x and y because you need x for the input and y for the output. Same thing here. You need x and y for the input and two other dimensions for the output. So it will be something existing in R4. Same thing for like if you have a function R3 to R2, you're taking three values. Your output is will be two values, and this graph of the function will be something in R5 because you need five dimensions. And they're all independent of each other to describe the information stored in the function in its entirety. Yeah, that's all I have. If you have any questions, feel free to email me. Otherwise, good luck with your problem set and the midterms coming up next week. Next